Welcome to my world. It's another period, another time, another day to really share knowledge. Knowledge is power, health is wealth. I have tried to now look at another topic of interest. I've seen that even as little babies, we are very curious, we are very observant. And if you can observe, you are more or less prone to be classified as somebody who have great interest in scientific findings, because our observations, we make inferences from our observation. But why it wouldn't be scientific is because of measurement. Because when there is no measurement, it becomes a problem. It is not provable. It is not reproducible. And that it was exactly the beginning of the having a uniform measurement that will allow for review, peer reviews, and many things like that. In the beginning, it was everybody, even locally. These days, we can see where people use certain tin, tomato tin, to measure the number of dericas in a bag of rice, and that will inform the measurement that will tell them that yes, this bag is accurate. So in measurement, you are thinking of accuracy, and that is why the scientific importance of accurate measurement is what I want to talk about today. Okay. So the topic is titled Accurate Measurement in a Medical Lab. Okay. So now let's go into the objective of the study today. When we talk about measurement, there is a need for us to understand that measurements have been done from time immemorial, but it's very local. It is not helping the growth of science, especially peer review. But the real progress in science started with these international measurements. But we need to look at the historical perspective to understand more. So the objective of this talk, it's stated below, to examine the historical perspective of measurement with the aim of explaining that science without measurement is a myth. To expose the two factors of measurement and why they are very necessary to note. To pinpoint the usefulness of accurate and precise measurement in medical laboratory for very essential for valid conclusion, and to list out the 5 types of measurement. The objective 1 states clearly to examine the historical perspective of measurement with the aim of explaining that science without measurement is a myth. You cannot go anywhere. You cannot really experience the astronomical growth we witnessed in science in the 70s. Before 1790, measurements were done locally without universal standards and created confusion in comparison across country and countries. So trade was very difficult because you could be easily cheated. There should be a universally acceptable measurement for whatever we are transacting. In 1790, the metric system became the first common system of measurement using the meter, kilogram, and seconds, and later amperes in international trade and also scientific reviews. The Committee of French Scientists, after the French Revolution, brought this about. In 1875, there was the International Treaty of Meter, which the United States originated to refine the metric system accuracy. Based on latest scientific knowledge, the CGS, that is centimeter, grams, seconds, came into use because scientists needed smaller units. You can understand, centimeter is 100 of a meter, gram is almost 1,000 of a kilogram, and many things. We even now talk about nanometer, which is our billionth of a meter. In 1960, a major revision resulted in the creation of the XI unit, named after the French System International. Other countries led by the United Kingdom abandoned the older unit of measurement and keyed into the measurement. In In 1971, the United States also allowed voluntary conversion to metric units, and that was an experience for 10 years. In 1975, President Gerald Ford signed the metric conversion act. It's also a voluntary thing, and the SI unit is intended to be evolving. It's an evolving system that, from time to time, based on it, there is a general meeting called to ratify and accept what to do. Its unit definitions are modified through international agreement. Now, Objective 2 states to expose the two factors of measurement and why they are necessary. Why are they necessary? These two factors are accuracy and precision. Accuracy means represent how close a measurement is to the true value. Precision measures how close results are. So when you do so many tests, so many results, you compare it to the true, but how close. That's when you are precise. When you look at this picture, you can see that this is the center point where the true result should be. But with continuous testing and code, you will find it scattered. But this is accurate to an extent, but not precise, because it's within the center. That's why it's accurate, but it is not precise. You can talk of precision here. Every dot is centered, so there is a little deviation, but it's centered. So we call this precise and accurate. This one is not accurate, not precise, and this one is precise but not accurate, because they continue to have the same thing. There must be a reason, which a very good scientist will always explain. The establishing performance standard is what would help you have accurate and precise results. So before a test method is used for patient, the lab must first ensure that the method is working reliably, that is accurate, and that it can be performed within acceptable limit of variability. There must be variation, but it must be acceptable. Coefficients of variation is also used to assess the precision under optimal and routine conditions. These are things we do so that that precision, the result you are giving is acceptable within the quality control measurement you adopted. Errors of inaccuracies or bias. Bias is usually the human error. Are regular with all test results. That is, when I talk of bias, we are talking of the performance of the test. With all test results differing from the correct result and must be kept at a minimum. Yes, you can see the other chart I show you. Standard deviation is more or less the deviation from the means, and very useful in setting up daily quality control charts. So, as a medical laboratory scientist, or all scientists generally, they must set up a control measure so that whatever they are doing is acceptable. Objective 3. To pinpoint the usefulness of accurate and precise measurement in medical laboratory to valid conclusion. You can never have a conclusion that is acceptable when all your methods are not accurate and not precise. So what can you do to know your measurement is accurate in the medical lab? I've almost explained earlier, but let us continue to look at what we can do. Calibrate your instrument. That is very necessary. You must calibrate it so that you know that what is given, 1 mil is 1 mil. The length is correct. What do you do? What you do to the test, you do to the standard. That is enough. The standard is supposed to help you because you know the value. It's supposed to help you to know the test. So if your standard, it doesn't go through the same experience of your test, whatever deviation you have with your standard may not reflect. So whatever you do to the test, you do to the standard so that you can conclude. Your conclusion can be valid. Do internal quality control and a role for external quality control apart from the checking the biasness of your measurement. Validation of results is also very helpful. The essence of accuracy and precision is to reduce error margin and allow for reproducibility and reliability of results. It helps the scientists to reach a valid conclusion. Result will be useful for, very, very useful for research. Errors of impression, that is, which could be general, is not necessarily the performer of the test that has this error. Incorrect and variable pipetting and dispensing, that is a general error which may not be limited because the pipette is not itself functioning well, it's not the performer of the test. And whatever is dispensed, especially these days that you have automation machines, so you are now talking of even the pipetting and what the machine is itself doing. Inadequate mixing of sample with reagent, this has very little to do with measurement, but when it's not well mixed, you can understand. Individual items of glassware or plasticware are not clean or dry before use. Dilution, your measurements could be diluted. So these are very useful, errors that we could take care of. Erratic performance of measuring equipment, like wavelength measure using chronometer. When you are talking of this, you are talking of when the thing is not, the machine itself is not reliable. That is, it's not reproducing the same results. It's very erratic. Then we are talking now going to bias, error of inaccuracies. When is bias? Incorrect calibration of the test method, which I have mentioned earlier. Tests being read at the incorrect wavelength or the wrong filter being used. An automatic pipetter is used that has been set to measure an incorrect amount. That is part of validation of and calibration of equipment. Consistent calculation error, that where the factors, the person is using incorrect factors and you will always get incorrect results. Use of unsatisfactory reagents, these are far away from measurement, but it will affect measurement. Objective 4, to list out the 5 types of measurements. This, the indirect method of measurement, example comparative, you can understand when you use the weighing, even METLA, it's an indirect, it's not so much like the one you just look and the thing pulls the weight down, hook balance, but where you are indirectly weighing the METLA. There is direct method of measurement using the vernier caliper, the micrometer, and the coordinating measuring machine. It is also with microscope too, because when you slice it, your section must be thin enough to be visible, so it must be very accurate even in histopathology when you are doing histology slide. Fundamental method of measurement using a fixed point instrument to measure temperature. So that is part of it. Substitution method of measurement, weigh on pin balances.